Okay, chapter 6. Chapter 6, factoring. I said this in a previous video. Excuse me, but I want to go over this again. Ready? Here's the question. Factor this number. So what do you say? You say 5 times 2. Great. Good job. Okay, factor this number. Factor the number 21. You say 7 times 3. Most people seem to know how to factor at least numbers if you ask them. However, what if I ask you, give me a definition of what it means to factor something, or, define or explain factoring? They're kind of caught off guard. They can do it, but they have a hard time explaining it. Well, just consider the following. If I had gone this direction, we would call that multiplication. So what is factoring? That's this direction. Factoring is the reverse of multiplication. And if you think about it, it really is, because how come you were able to factor 21? Because you knew that 7 times 3, 7 multiplied by 3, was 21. Now this also gives us some other insight. What is your procedure for factoring? What technique did you use to factor 21? Let me give you another example. Here's a number to factor. 5,300,791. Ready, set, go, factor it. Now, what am I getting at? What I'm getting at is you actually don't have a procedure. You were able to factor 21 because, frankly, you just knew that 7 times 3 was 21. And you were able to factor 10 because, let's just face it, you knew 5 times 2 is 10. And you can't factor this one. I mean, I don't know whether you can or not. I don't even know if it's factorable. I don't know whether this is a prime number. But you'll notice when someone says factor this, you feel caught off guard. You're not even sure what to do. And more or less, I'll tell you the current state of affairs. People are always thinking about it. Not lots of people, but some people are thinking, is there some efficient procedure? Is there some quick procedure to factor numbers? And the answer is no, there isn't. At least, well, I mean, there might be, but no one's discovered one yet. And the only procedure we have right now is basically trial and error. Does 2 divide into this? Does 3? Does 4? Does 5? Does 6? And you keep on going. One of my favorite examples is 51. It just sort of looks prime-ish, but it's not actually prime. It's 3 times 17. And hold on a second. Good, this is off screen. You won't be able to see what I'm up to here. So I'm up to something. Just hang in there for a second. Where'd we go here? Blah, 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 blah. Okay. Wow, it's a lot of quiet time here. Hold on a second. Okay, factor 9,167. Now, the only way you can really go about this is to ask yourself, does 2 divide into, does 3, 4, 5, 6, 7, 8, 9? And it would seem hopeless, except if by some, I don't know what, miracle, you were incredibly tenacious, and I don't know why anybody would do this, but you got all the way up to 89, you would find that 89 does divide into this. And that this number is 89 times 1 and 3. Now, what was I up to a minute ago? I was reaching for a calculator, and I took 2 prime numbers. I think those are prime numbers. How many prime numbers are there? Infinite number. Do I know them all? No, you can't know an infinite number. Hey, that was proved over a couple thousand years ago. I won't torment you with the proof. But there are an infinite number of prime numbers. As far as we know, see, some of these things are not known. As far as we know, there's no regular pattern to the prime numbers. 2, 3, 5, 7, 11, 13. In my head, I'm just going 13. Okay. Is 14 a prime number? No. 7 times 2. Is 15 a prime number? No. 5 times 3. 16? No. 2 times 8. 4 times 4. 17, 18, 19. But there's no pattern. It might seem like if you wrote down the first 20 or 30 prime numbers, maybe you think you would have detected a pattern, but there isn't a pattern. There's some suggestions of patterns, but as far as we know, there isn't one. This is the only way to determine this. It's horrible. Now here's the good news. We're never going to have to do anything like this. Now a computer can do this fairly quickly, fine. But if the numbers get big enough that even computers get bogged down, and that's the basis for 128 bit encryption, or some people call it RSA or public key access code. None of that applies to our course here. But what on earth was the point of me telling you that? The point is this. We're not really going to have a method for factoring. I could pretend like we had one. I could lie to you, but there really isn't one generalized procedure for factoring, except for what I just showed you for numbers. Now we're going to be factoring polynomials, so let's consider what would that mean, and then I want to explain what on earth do I mean there's no procedure. And I do mean that. So you're not supposed to see this. I want you to see this. Take a look. But you're not supposed to see this. But take a look anyways. So 3x plus 1 and 2x, let's say minus 5. Now, you see that? Pretend you don't see that, but see it anyways. Okay? So what is this equal to here? Let's do the good old FOIL method. So 6x squared. And that would give us negative 15 plus 2x, so negative 13x minus 5. But you weren't supposed to see that, because what I just did was multiplication. But now what I want to ask you to do is to factor this. And factoring, as I said, or like I said, is the reverse of multiplication. What is the procedure for factoring this? I'm going to level with you. I'm going to tell the honest truth. For a second order polynomial like this, there is a procedure, but we're not going to cover it. It's a little bit beyond the scope of this course. Here's what we're going to do. Guess. Or I could call it trial and error. Or I could try to pretend and make it seem as though there was some sort of procedure involved here, but it really involves trial and error. Now, hopefully by now you forgot what I had written up there. I know I forgot what I had written up there. So when I look at this, I think to myself, well, this is clearly the result of what you get when you do the FOIL method. No question about that. The only thing is I don't know whether we're supposed to write 6x and x or 3x and 2x. And well, maybe you remember what I had up here, but remember you weren't supposed to see that. Now, first, you absolutely will not know which of these two it is. And it turns out either one might work, or both might work. But let's say you gravitated towards this one first. Now maybe, I kind of do remember this is what I have, but okay, fine, you're not supposed to see that. So let's go to this one first. Now, think about when you do the FOIL method. How do you get this number here? It's the product of these two numbers. So this must be either 5 and 1 or 1 and 5. And then I have to make decisions about the plus and minus. But let's just say, because I said guessing, let's just say I put 5 and 1. Now think about the FOIL method for a second. You have 6x squared, it checks out. 5 times 1 is 5, and we can negotiate or make allowances for this negative sign here. But the outer and the inner two, look, you've got 6x and 5x. Well, 6 plus 5 is 11. 6 minus 5 is 1. 5 minus 6 is negative 1, and so on and so forth. I don't see any way to get a 13 out of that. So this does not look promising. You could continue on all the way to the bitter end. For example, you could say plus minus or minus plus or minus, whatever you want to do. None of it would work. So you abandon that effort. Now maybe you try 1 and 5. Well, okay, fine. 6x times x squared, the 1 and the 5. We could probably get that to work out. 31. Well, 30 plus 1 is 31. 30 minus 1 is 29. This doesn't look hopeful at all. So I maybe abandon this entire approach. Now I come down here. Let's see. Suppose I put a 5 and a 1 here, and a minus and a plus here. And so what I'm doing is I'm making a guess. I'm guessing. More to be said on guessing in a second, but right now, what would you have? You'd have 3x times 2x, 6x squared. Sounds pretty good. Look at the very end. Negative 1 times 5, negative 5. So we're hopeful. We're filled with anticipatory glee here or something along those lines. But uh-oh, look. 15. Oh, wait a minute. 15x minus 2x. Well, 15 minus 2 is 13, but son of a gun, we wanted that to be negative. So maybe we switch these signs around. 3x times 2x, x squared, 3x times -5, -15x plus 2x. Bingo, check, whatever you want to say. 1 times -5. So this checks out. Boom, we got it. Unbelievable. How did we get it? Sort of, I want to say sort of educated guesses. I mean, if you burrow down deep enough into what you're really thinking, it's actually very interesting. I mean, like 6 is 3 times 2 or 6 times 1. How do I know that? Pure memory. But that doesn't necessarily explain how that's even encoded, you know, up here. But at any rate, it is for the time being. There we have it. Now, this may seem like, again, we're just guessing, and the answer is yes. So let me do another example. Suppose we had this. Okay, let's say we had a, I don't know, 7x plus 2. Use a different marker here, a little bit better marker. 7x plus 2, and let's say 2x minus 3. But, you know, again, you're not supposed to see that, but I kind of do want you to see it. This times this, 14x squared, fine. That negative 21 plus 4. So negative 17x, and then minus 6. You weren't supposed to see this, so sort of, I don't know how to indicate. I want us to be able to look at that, but you're not really supposed to see that. So when I look at this right here, I look at these numbers initially, and I have to say, amongst my two choices, 14 and 1 versus, I feel a little more optimistic about this, because 14 times some other number, maybe it gets you kind of a large number and it doesn't look promising to get the 17. Now what I'm really saying is, it's the fact that I've done, you know, I don't know how many quadratic second order polynomials. They're also called quadratic polynomials. When we get to quadratic equations, we're fully going to talk about this. I think I already talked about it a little bit in the previous video. But how many of these have I done? I don't know. Hundreds of thousands at least. I don't know, 1 million. I'd have to think about that. But at least 100,000. I'd have to do some math to figure that out. You know, how many on average per day, per month, per week, per month, per year, over all these years. But I've done a lot. So what that means is, I don't want to say at a subconscious level, but maybe almost at a subconscious level or at a conscious level, but very rapidly, what I'm doing is I'm testing a lot of options quickly in my head. So what can happen is, remember, pretend you don't see this up here. You may have a teacher, and the teacher says, okay, let's factor this. Well, 7x, 2x, and they look at it and they say, well, 3, 2, minus, plus, and we got it. And it seems like, wow, how did they do that? That was incredible. You did it really fast. You know, what's your secret method? Secret method is do a lot of them. Oh, it's a horrible secret method, but yet that is the secret method, is to do a lot, and you get the hang of it, and you get good at it. And a lot of people don't want to hear that. Now, if you're listening to this, and you think you have a method, or if you're talking to someone and they think they have a method, they know how to factor these, the first thing I would suggest is the following. Let me write this in a easy to read. Here we go. Ready, set, go, factor that. Well, I've done this in classrooms a lot of times, and I usually wait a couple of minutes and everyone's scribbling away and they're frantically, or not frantically, but hopefully they're trying to factor this. Now look at this one right here. The numbers are much easier than the one that I did a minute ago. Much easier numbers. So, wow, this should be really, really easy. And you try a bunch of things, and the things that people always seem to try is this seems to be like a favorite to try, but if you test this one out, look, x times x, x squared, this times this, negative x plus x. See, it's not going to work right there, but you get x squared minus 1. So, nice try, you know, but it didn't work. And I invite you to go ahead and try a whole bunch of other things. I'm going to tell you right now the following fact. This is factorable, but not in any particularly easy way. I mean, this is not super, super difficult, but it's not an easy way, and it's not a way that we're even going to talk about right now. So what you might see in books and what you might have heard from teachers is this is not factorable. Now, it is factorable, but it's not factorable in the following way. It's not factorable where this number and this number are going to be whole numbers. This is factorable, but these will not be whole numbers. In fact, they won't even be rational numbers or fractions. What that means is, at that point, guessing is no good. Trial and error is no good. The way I just said is trial and error, get practice or get good at it. That falls apart. You can't do that anymore. So for right now, I feel very hesitant saying this. See, books will say this is not factorable. It is factorable, but it's not factorable if we restrict ourselves to whole numbers. If I require that this and this be a whole number, then it's not factorable. But there is actually a method for factoring second order polynomials, and it would give us an answer. So if you think you know a method, you should be able to apply it here. Or if you're talking to anyone who tells you a method, I don't even want to go over any of these sort of quasi or fake, really phony methods. There are some methods, but the reality is they barely ever work. They may work if I give you really nice examples, but in general, they don't work. And you can have them tested out on this. And the situation gets much, 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 much worse. If I were to write this down, wait, that's actually not much, much worse, and we'll find out why. Here, let me write this down. Here we go. That is factorable right here. But this took mathematicians around the world over 3,000 years to figure this out. Now I'm going to talk much more about this later on. So if you think you know anybody who has a quote unquote method for factoring things, if you want, this is a little bit mean, but if you run into someone and they say, well, yes, I know how to factor things, say, well, could you please factor this? It does factor. Hey, no fair, you can't let them use software. Yes, our computer program. Yes, this is factorable. Yes, there is a way to factor it, but it's really, really, really complicated. And so kind of no fair letting the computer do it. That's not what I had in mind. And then if you wanted to be, ultimately mean, is this factorable? Yes, but there's no method to do it at all. In fact, that was proved, that was demonstrated around 1800, around 200 years ago. More on this later, but by a young Frenchman named Galois. And this actually, you can prove it is factorable, but you cannot find the solution to factoring this. And there's some caveats and catches in there, but we don't need to worry about those right now. Okay. Well, you need to worry about, and I need to worry about, and we all need to worry about it first and primarily is factoring second order polynomials. Now, what makes it a second order polynomial? I know I said this before, but it's where you have x to the power of 2. The highest power of x in the polynomial tells you the degree of the polynomial. So it's a second or third or fourth or fifth order. And this is also called quadratic for reasons we'll talk about later. I think I already talked about. And if it's a 3, it's a cubic, and a fourth, it's a quartic, and fifth quintic, and then I don't know. This is a variety. Nobody, as far as I know, uses the words after that. It's just 6th order, 7th order, 8th order polynomial. This is the most important class of polynomials, second order polynomials. So we really, really do want to become good at this. Now, how do I make up examples that are factorable? Let me show you the behind the scenes here. Again, you're not supposed to see this. But if I write down a random second order polynomial, it either won't be factorable with real numbers, or it definitely won't be factorable with whole numbers. But I want to give you problems that are factorable with whole numbers. So what do? I make up something like this. Like, let's say 3x plus 5 times 3x plus 5. Now, you're not supposed to see that, right? I'm going to go ahead and multiply it out. We see what we get here. 9x squared and 15x, 15x, 30x, and then plus 25. But I don't let you see that, and I tell you to factor this. Or let's just say, for example, I told you to factor that. Now, both of these are what's called a special case. And maybe let me discuss that at first, but no, later. Because what I think is important to do at first is to struggle through the trial and error of factoring these. You just keep trying and trying and trying until you get factor. Now, we know the answer here. And so I can't help it. The answer here is, because I just had it written down a second ago, it's 3x plus 5 times 3x plus 5. How do you write it in a more compact or simplified way when you have something times itself? Well, you just write it like this, squared. And this right here, I mean, you might have seen this before, you might not have seen this before. I don't really know, but if you think about this and you struggle through this one enough, what you'll see is it looks like this. Now, turns out, see, I don't know if I should tell you this or not. I think the best thing to do is to have done a lot of FOIL method problems. So, assuming you've done this like you were supposed to, back in the last chapter. So you were supposed to have done a lot of things like, say, 4x plus 5, and then 4x, let's say, plus 5, such as this. And the answer here would be, let's see, 16x squared, and then plus 40x, and then plus 25. And if you did a lot of these, what you would have seen is that when you have copies, that you would get the first thing squared plus twice the product of these two plus this squared. It was a lot of words. Let me write it down. Let me write this down. I want to write down in symbols what I just said. You would get the following. You would get this. Is this important to know? Actually, yes. I hate memorizing things as much as anybody I know, I think. So if I say yes, should you have this memorized? Should you have this locked away in your mind? So if someone were to ask you this, you would report this without looking at anything, notes or books or anything. My answer is yes. And I don't say that too often. So I'm just saying that to try to indicate, yes, this is really important, this product right here. So that when you look at something, and I'll just write down any of two, let's say 3x minus 7. Here, I'll just write it like this, 3x minus 7 squared, that is 9x squared, and then multiply these two, 21, but double it, so minus 42x. Sorry, that doesn't look like very much of a 2. And then this plus 49. It is important to be able to do that and in both directions. So here we have multiplication, and coming back this way we have factoring. So that you can go either way and that you recognize those patterns. And similarly, if you had multiplied many, many things that look like this, a plus b times a minus b. Now, these things are called conjugates of each other. That is actually a word worth knowing. Again, I'm not really big on vocabulary, but there are some terms that, yeah, you do need to know. I mean, you just, I don't know how else to say it. Like, if you don't know this word conjugate, eventually it's going to make your life really, really tough. Now, an object is not a conjugate. They're really a conjugate for each other. It's like having a sibling. I mean, just a single individual living organism is a sibling. It has to have a sibling to be in relationship with. So these two are conjugates for each other. And when you multiply them out, you should verify this. Whoa, you get minus b squared. Huh? That's comical. I almost write down the wrong thing. This. So when you see something like this, and you will, so say 5x plus 7 times 5x minus 7, very rapidly you can write down 25x squared minus 49. Here, I'll get out of the way here. And these are shortcuts. And just like I said, I hate telling people to memorize things, but some things, yeah, you should just know. And I'm not really a big fan of injecting vocabulary words into a subject unless it's necessary. There are some words you should just know. And I'm not a big fan of shortcuts, but there are some shortcuts that, yeah, you do want to know. And these are two of them. And these are usually called special products because, look, going from here to here, that's a product. Going from here to here, or yeah, from here to here, that's a product. We're multiplying. Okay, we're about done with this video here because there's more to be said on factoring, and we have to talk more about factoring, although this really is the main thing. And factoring is chapter 6, and it's really important that you practice chapter 5 and chapter 6. And I put another announcement about office hours for you to suggest sometimes that might work better than the Fridays. I'm going to continue the Fridays, but I can have a few more hours here and there if that works better for you. There isn't a lot of theory in chapter 5 and 6. Really, I mean, the theory is fairly minimal, but it's a matter of practice, 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 and developing these skills. It is fairly tedious. You probably don't feel like you get any deep insight, and that's kind of normal. We got some, from my point of view, what's coming up, much, much, much more interesting. But these are necessary skills that you really got to have to move on ahead. Let me just, this is just kind of, I was going to say apropos of nothing, but it's apropos of what I just wrote down. Here's a secret little trick. I used to say, at a cocktail party, you could dazzle your family and friends. Let's say this comes up, and you might wonder, well, how on earth would this ever come up? I don't know, but you suppose this came up somehow. And someone said, what's 41 squared? I don't know if I'm really in the mood to think this over right now, but I could probably give the answer pretty quickly. And let me tell you how I'd be giving the answer pretty quickly. I would think of this as 40 plus 1 squared. And then I would use that special product because that's 40 squared. That's easy to do. That's 1600 plus 2 times 40 times 1. That's pretty easy to do. That's 1680 plus 1 squared. So it's 1681. This is all pretty easy to do in your head. Now this sort of works if you're really under 100. It's a little less easy to do in your head once you get over 100. And also it's a little bit easier if you're not too far away from a multiple of 10. Let's say you had 48 squared. Now what I would probably think of this is 50 minus 2 squared. And that's 50 squared minus 2 times 50 times 2 plus 2 squared. This is 2,500. If you think about it for a second, this is 200. That's not too bad. So 2,500 minus 2,000 is 2,300, 2,304. Is this a trick you need to know? You got to be kidding me. Absolutely not. No way. It's just some little trick I picked up along the way. I don't know. Do I use it? No, not really all that often. It just cracks me up. If this was the reason to know a special product, I wouldn't even bother with it. Let me tell you that much. Okay. So factoring, it takes practice. We'll do more practice. We have a test this Friday. Remember, I think that's October 30th. And it's going to cover, what chapters is it going to cover? I think chapters 5 and 6. I'll have to double check. It's the announcements under the syllabus update, but I'll double check that. But chapters 5 and 6. So it's all things polynomial. In particular, multiplying and factoring and the rules of exponents. Again, remember, I went over the rules of exponents. There's no more theory to be said on the rules of exponents, but you need to practice, 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 practice. And here's the key thing about office hours. If you can't get some of the problems or confused, ask me, and then I'll go over them. It can seem like there's just hundreds and hundreds of problems. Honestly, the more you do, the better you'll get at them. There's no two ways about that. Oh, I'll leave that for next video. I want to do a video on scientific notation. But I'll finish this one off for right now. Okay.